So now let me call this, let me give a name for this. It's called null of A, okay? Because it is those vectors that when operated by A will give me 0. That's why it's called null. Okay. So what can you say about this set? Definitely, if this set is only 0, it contains only singleton, just 0 vector, then we can hope to invert A, right? First of all, even if m equal to n, you can hope to invert A. Otherwise, if this is not just a singleton, let's say it contains few other vectors also, then definitely A is not invertible, right? That is very clear. So what can you say about this null of A? It's also a vector space. In other words, null of A is a subspace of Rn. Okay, so claim null of A is a subspace of Rn. So how do you show this? How do you show? Well, this is what we have, right? So it's a subset of a vector space. If I have to show that it's a subspace, all that we have to do is show that it's closed under linear combination. Okay, so that's easy, right? So how do you prove this? Proof. You take any two vectors and two numbers, right? Let's say uv belong to let's say null of A and alpha beta belong to R. You take two numbers and two vectors. Need to show that the linear combination, that is alpha u plus beta v, belongs to null. That's all I have to show. Now, can somebody think of a proof? How do you prove that this is true? See, A is matrix and it's a linear transformation, right? So I can replace A by a linear transformation. That's what you would have studied in your linear algebra, right? So they always like to think of these things as transformations, not really as matrices, right? Although it turns out that both are same in this case. Yes? Well, what can you say about U? U is in the null of A. That means AU is, what can you say about AU? 0, because U is that vector which gets mapped to 0, right? So this is 0. What can you say about AV? 0, right? This is because of the fact that U and V belong to null of A. So this means AU plus AV, sorry, alpha times AU is also 0, beta times AV is also 0. Do you agree? Right? So now what does this imply? This implies I can push alpha into inside, right? So alpha times U. U is a vector, alpha is a number. I'm just scaling it, still 0, right? A times beta V is also 0, right? What does this imply? If I add them, I should get 0, right? So A times alpha U plus A times beta V is 0. Well, A is a linear transformation, so A alpha, A V plus let's say U is A times U plus V, right? So it's A times alpha U plus beta V equal to 0. That means, well, this is also a vector, right? Do you agree? This definitely belongs to Rn, right? It's a n length vector, so this definitely belongs to Rn. Now I'm saying it is that vector which gets mapped to 0, right? So what does that mean? This is easy, right? It belongs to null of A. So null space is a subspace. Okay, this is something that you should always keep in mind. Is that clear? Any questions? Okay, so now we know something about the null space, right? So let me look at the picture again. So you have this Rn. Okay, so you have this Rm here. And now I looked at some subspace here, right? This subspace. All of them get mapped to 0, right? 1 point, right? This is a subspace. Okay. Now, if it is a subspace, it's a vector space. So I'll have a basis, right? Do you agree? So let's call this basis as V1 through V, let's say K. Okay. There are K vectors. That means it's a K dimensional subspace. Suppose, okay, K could be 1 to any number less than or equal to n. Okay. So now you have this vector space and you have the basis. So now if you look at the entire Rn will also have a basis, right? So now the question is, can I add a bunch of more vectors to this to get a vector space of the entire Rn? Is that clear? Is that fine? Can we do that? For example, you have R3, R2 is a subspace, you have a basis, right? What is the basis for R2? When viewing it as a subspace of R3, what are the bases? So suppose you have this, right? So, right? So now if I look at R2 as a subset or a subspace of R3, then this is 1, 0, 0, right? This is a standard basis or standard vector, right? This is 1, and if I call this as my xy, this will be 0, 1, 0, right? These two are basis for R2, but if I want to get a basis for R3, what should I do? I should add one more element, right? What is that? 0, 0, 1, right? If I add this, I'll get the basis for the entire space, right? Similarly, if I have a null set or null of A, which is a subspace, I have a basis, which is this. Now what should I do? I should add a bunch of more vectors to get a basis for the entire space. Do you agree with that? Okay, so now I can do this, right? So V1, well, by the way, I'm really sloppy here, but we should be okay, right? And I can add, let's say, vectors like U1, U2, etc., UL, okay, to get the basis for Rn. Well, K plus L should be equal to N, okay, so otherwise this is not true, right? I'm going to add more vectors so that the total number of bases is equal to N, which is the dimension of Rn, right? Is this clear? But how do you prove that this is true? Well, do you remember replacement lemma? How many of you know replacement lemma? Meanwhile, I'll check if everything is fine here. Okay. So what is replacement lemma? I have two sets of bases, right, of a vector space. I can keep on replacing this by one of these, replace this by one of these, and keep on doing that, right, until I exhaust the entire thing. I'll replace, right? Do you agree? So similarly, can you think of this extension as a replacement? So for example, I have a set of bases for the entire Rn, right, and I have a basis for the subspace, right? So what am I going to do? I'm going to take one of the elements in Rn, replace it with one basis of the subspace. The second basis I'll replace, third basis, and so on. I'll replace everything, at least a bunch of it. Now what do I get? I still have a basis for Rn, right? So now a part of it is a basis for subspace, and the remaining is something that I have added. I can think of it like that, right? So replacement lemma will be useful here. You can show that, you can extend. I'll leave that as a homework. You should think of how to do that. Okay, formally you should be able to write. Okay. Anyway, so this is the entire space, right? So I can extend this.